इंट्रोडक्शन में क्या नहीं ना
Hello. Say again. Hello. Okay.
Younger guys don't know who you are.
Okay.
Yeah.
Okay. Thank you. So, shall I get started then? Okay. Very good afternoon. I'm Chetankumar Jalihal. So, I'm an alumni of COS. I was here for my master's in 2013. That's now 12 years ago. So, after my master's, I also have, I did my PhD here at COS. And then I moved to Max Planck. So, that is where most of what I'm going to present today was done. So, it was done with Uwe Mikolajewicz. So, this is what I have for today about monsoons and deserts. So, before I get into that, a little bit about what's been happening recently. So, this was on 16th May. Look at the time, it's 1 a.m. So, on 15th May, IMD released the forecast, onset forecast, and the Hindu picked it up and have published an article the very night. So, back then, IMD was expecting monsoon onset over Kerala on 26th of May. So this is an early onset. Usually we have onset over Kerala on 1st June, so this is earlier by 5 days, right? So when this report was released by IMD, the media was very quick to pick it up. So this is one example. Few hours later, in the middle of night. So subsequently, other news outlets have also picked it up. So it was quite a buzz, right? So here is a nice graphic based on some of the data last week. Jace had discussed some of this thing. So this is from Times of India. They have made this graphic. The last 20 plus years of performance, IMD performance, forecast performance with respect to monsoon onset over Kerala, right? So in blue is the actual onset date, and in red is the forecasted onset date. So for most of the years, they get it right. The error is roughly within plus minus 4 days. I think one of the major errors was in 2015. The error is roughly how many? 6 days. So that was the biggest error they had until this year. So this year, they later shifted their own forecast, onset forecast day from 26th to 6th June and then to 4th of June. So there was quite some changing around. So now 4th of June is the official onset date over Kerala. So the blue line is what we should be looking at here. So this year, the error has been 9 days. So that's roughly double the typical error that IMD gets. So there is a good reason why IMD made that forecast. If you look at the monsoon onset over Bay of Bengal, the red line, 22nd May is when monsoon is somewhere over here. This year, monsoon was there already at least 1 week before. That's around 16th or 17th of May. Now, it is unfortunate for IMD that monsoon did not progress further. It remained stuck somewhere over here for the subsequent days, and eventually onset occurred over Kerala on 4th of June, and then the progression has been rapid and it has made up for the delay. So right now, around 10th of June, so monsoon is somewhere over here, which is roughly the climatological onset isochrone, right? So if we look at the actual map, this is a few hours ago. So this is OLR, the blue imagery. You can see a sharp gradient in clouds over the southern peninsula versus the northern India, where onset has not yet occurred, right? So onset region, where monsoon onset has already occurred, no onset yet, very dry and arid. And if you have been following news, you already know that North India is suffering from extreme heat, right? So this is the medium range forecast that IMD had released on 28th or 27th of May. Back then, their model was still suggesting no onset possibility between 4th to 11th of June. You can see large negative anomalies over southern India, especially around Kerala. And uh, going further from 2 weeks to the third week, it showed some onset in the third week. So the model forecast capability beyond second week is already beyond 1 week is unreliable. And that is what we see over here. I mean, comparing this with what has already happened in the last 1 week. So this is what was released last week. So this is from 4th of June to 11th of June. You can compare this with this and you see a very big difference. So highlights how how bad week 2 can be sometimes. But the good news, hopefully, is that this onset progression continues and continues through June. And probably by the end of this month, we will have onset all over the country. So basically, after a 4 days delay, the monsoon progression does not seem to have gotten affected. It probably has picked up a little bit. So we have the nearly coverage over the whole country, monsoon coverage over the whole country within around this month. So one more interesting fact is that this is temperature from ECMWF at 1 p.m. today, right? So this is not exactly observation, but this is very close to it. So let us assume this is representative of that. So in southern India, there is relatively low temperature. Of course, the Western Ghats elevation, that effect you can see over here. But what is striking is that North India is probably hotter than Sahara. It is almost at par with Middle East. So this is not a one-off event. This is something that happens almost every year. So this animation here is monthly climatology, surface temperature, right? So as the months progress in this animation, you will see that, okay, so this is right now October, November, December. So during the winter months, India, Middle East and Sahara are almost similar temperatures. But come May, June, North India is hotter than Middle East and some parts of Sahara. So this is a regular thing that Indian subcontinent is hotter or just as hot as the deserts to its west, right? So monsoon or Indian South Asian monsoon is in subtropical latitudes where we have most of the deserts. So monsoon is an anomaly to this desert. Had it not been for monsoon, we would have deserts in this region as well, right? So monsoon is the anomaly to the general rule of subtropical deserts. So what I'm interested in is this transition. Pre-monsoon, there is very little difference between Middle East, India or Sahara. But come monsoon, there is a major transition that occurs, and I'm interested in this transition. The transition phase is roughly about a month or two, starts before the onset itself, and then progresses through onset into the monsoon phase, end of June. So I'm very much interested in that transition. How does that transition occur? Uh, what what are the conditions that create this transition in a region which seems very similar to a desert prior to the onset? So to understand that, I want to make a small digression and talk about a common theory that connects monsoons and deserts. So to understand this, we have to go back to this paper, Nealon and Head, 1987, where they made a proposition that low-level convergence, mass convergence, can be expressed as a ratio of these two quantities. So let us break it down. So this guy here, that is low-level mass convergence. 2 here, subscript 2 refers to the lower troposphere. There is a negative sign. So this is divergence of mass and a negative sign. So it is referring to convergence. Okay. On the right-hand side, there is F TOA, F surface. So these are the energy fluxes from the top of atmosphere and the surface of the surface into the atmosphere. and a term called GMS, gross moist stability. Now, originally in the paper they have this equation. Low level mass convergence is F bottom F2R. The signs have been accordingly adjusted, and this term here, that is GMS. So originally GMS was proposed as this quantity with some parameterization. So this is dry static energy difference between the upper troposphere and the lower troposphere. So kind of represents vertical moist stratification, dry stratification. And this thing here, that is the moisture content in the atmosphere. Now they have made a parameterization for this moisture content in the atmosphere. So why that is important, you will know in a few slides, but just remember that there is some parameterization involved here. Now these parameterizations are not involved in our calculation of GMS. Okay, so that is important. It's a small minor detail, but that is important. We will see later. So let us spend a moment on this schematic over here. There is energy fluxes going into the atmosphere from the top, from the surface. There is convection, right, and rainfall. Now energy is being pushed into this, energy is converging into this domain. There is updraft and then divergence at the top of the atmosphere. So this is a typical monsoon circulation. And this equation is meant, or these two equations are meant to describe this type of circulation. So there are two key assumptions here. It's a steady state atmosphere and a two-layer atmosphere. Okay. Now we are going to focus only on land regions. So Indian subcontinent, Indian landmass, Sahara. So F surface can be ignored, surface energy fluxes. So you have a simplification now. Mass convergence, low level mass convergence is F2R by GMS, right? So this is a very interesting equation. The numerator of this equation is all of the radiative terms. The denominator represents thermodynamic terms, and on the left hand side we have the dynamics coming into picture. So this is one equation that combines three important aspects of the atmosphere: atmospheric dynamics, atmospheric radiation, and thermodynamics, all three coming together. So that is the beauty of this equation. Now that equation originally Nilin and Held proposed for a region of convergence, something like this, right? So this equation, in my opinion, should work anywhere. So this is, for example, a desert region where you have upper level convergence and there is subsidence, and low level divergence. So there is divergence in the lower troposphere. So this guy here would be negative. Okay. So if this is negative, either GMS or F2R has to be negative, one of those two. Okay. So moving on, if we look at observation, you will see that monsoon regions typically have F2R positive and deserts usually have F2R negative. So this kind of goes along with what comes out of this equation, right? Now, interestingly enough, Nilin and Held have already made some, they already had some thoughts about this, but they did not pursue this further. So if you look at the statement here, they at some point say that deserts can be thought of regions where precipitation is zero, arid regions, right? And the reason why they did not pursue it further is that Q2 term which I said, which was parameterized, right? That parameterization breaks down in arid regions, and therefore they did not pursue this further. So in my opinion, this could have been one of the first propositions, a unified theory for monsoons and deserts, where you have a theory for low level convergence or divergence, relating that to atmospheric radiation and thermodynamic terms, right? But I believe going further back in time, in 1975, Charney had already made an interesting proposition that high albedo leads to enhanced radiative cooling and therefore subsidence. So although it was not formulated with an equation, that in my opinion was one of the first attempts in this direction. And subsequently, an equation for updrafts was proposed by Nilin and Held, but they avoided desert regions. With some correction to the moisture terms, we can use that equation very well. So that is what we will see today. So F2R, this is from era 5. June, July, August average climatology. All right. So the monsoon region, South Asian monsoon region, it's all positive values. Over Sahara, it is negative, consistent with the circulation in these two regions. Right. So one more thing that we can do, because we have that equation, uh, mass convergence, uh, energy fluxes divided by GMS, it is also possible for us to diagnose which of these two terms are important. Is the numerator important or is the denominator important? Important in what? In quantifying the difference between these two regions. Okay. So one of the things that could be done is, instead of using the low level mass convergence, we could also use moisture convergence, which is P minus E. Okay. So this is a slight modification of the same formulation. So this is moisture convergence over South Asia minus delta represents the anomaly between South Asia and Sahara. So this is almost zero. So this pretty much represents the rainfall or moisture convergence over this region. Now, when that is diagnosed as a contribution from the F2A or GMS, then the difference is very clear. Most of the differences between Sahara and South Asia turn out to be because of radiative fluxes, right? So, so it is basically a balance between, so it is basically a balance between the radiative terms and circulation. So it is for this reason that I believe monsoons and deserts are radiation circulation systems. Now, since F2R is the main difference between these two regions, let us diagnose further what causes this difference in F2R. So this is F2R difference between these two regions. It's in millimeters per day, but it can be easily converted to watts per meter square, a multiplication factor of roughly 29, 30. So the biggest term, so there are two things here, right? Reflected short wave and OLR. S in both of these regions is almost similar because they are at similar latitudes. So in the difference, this does not matter. It is either the reflected short wave or albedo, OLR. So a decomposition shows that it is OLR that is very important and not albedo. Now this is important because Charney had made a proposition that albedo plays a very important role in desertification. Now this shows that albedo is probably not that much important. It is the difference in F2R is coming out of OLR. Now we can further decompose OLR into clear sky, cloudy sky, and there are some other terms here which we can ignore. So the clear sky, cloudy sky components are nearly equal here. So here is a seasonal cycle, monthly mean seasonal cycle for three quantities, F2R, S1 minus alpha. So that is absorbed short wave, and this is OLR. Now there are two regions here, South Asia and Sahara. South Asia is in the solid line and Sahara is in the dashed line. Now, if you look at F2R first, during the non-monsoon months or during the non-summer months, F2R is negative over Sahara. It just barely becomes positive during the summer months. Now, we saw earlier that it is negative here, but when you take a area weighted average over this box, land only grids, there are some positive grids, and because of that, it tends to slightly go beyond zero. It becomes slightly positive. Over South Asia, it is negative during the non-monsoon months. Around the time of equinox, it starts to become positive, and then it is very large positive during the monsoon months and subsequently declines. So if you look at the absorbed shortwave component, the difference is not too much. There is a small difference during the non-monsoon month. This is where suddenly monsoon onset has occurred, clouds have formed, so reflectivity over India has increased. Reflectivity has increased, so absorbed shortwave is less. So you can see a sudden large dip over here. But despite this decrease, the difference here between South Asia and Sahara is not too much, is not as much as OLR is. So OLR is a very big difference here, right? The two regions have OLR diverging. And if you pay attention, the divergence already begins in the month of March, April, May itself. So the key here, the key difference. So let me summarize what we saw so far. We have a region where you have low-level mass convergence, a region where you have low-level mass divergence, monsoon and desert, respectively. And these two regions have their respective convergence or divergence proportional to the radiative fluxes at the top of atmosphere. Now, these radiative fluxes are mainly different between these two regions because of OLR. So that's a brief summary of what we saw so far. So the next question is, why does OLR change? Now, before I get into that, I want to summarize the main result that we got, and then I will show why OLR changes. So obviously, we saw here that there is clear sky, cloudy sky component, right? There is both contribution from nearly equal contribution from clear sky, cloudy sky. So I will first describe the process, and then I will show some evidence. Now, before monsoon onset, or slightly before the monsoon onset, so whatever I describe, I will describe it using this same equation. F2R has been expanded here, S minus alpha S minus OLR. There is some large scale forcing. I'm not going to say what it is. It could be land sea temperature contrast, it could be the movement of Hadley cell, or whatever. I'm going to remain agnostic for the purpose of this talk. Whatever is your favorite theory, you choose that. Now, there is some large scale forcing which will lead to low level mass convergence to begin with. Now, the moment you have mass moving towards South Asia, it is also going to carry water vapor. So moisture gets advected over this region, which has an instantaneous effect on OLR. OLR will reduce because water vapor is a greenhouse gas. Now, the moment OLR reduces, the numerator becomes bigger. So numerator is bigger, then circulation has to balance this. So circulation will increase. This will circulation will increase, which will advect more moisture into this region, which will reduce OLR further because there is more moisture loading. That will increase the numerator further, which then feeds back into the large scale circulation. So there is a internal feedback occurring here within the monsoon system, which helps in the growth of monsoon. So this process persists mainly during onset time. Now, there is one factor I have not highlighted, and it's a deliberate omission, the impact of GMS. Now, when moisture is building, GMS will also change. And after a certain critical threshold, you have convection. Clouds will begin to form. That is typically around the time of onset. The moment you have clouds forming, clouds will instantaneously have additional impact on OLR. They are also reflective. So albedo, the absorbed short wave, is also going to get affected. So then there is that another branch of feedback that gets initiated, which I am not so much interested at the moment. I am mainly interested in the feedback that exists between large scale circulation, moisture, OLR. And that feedback exists primarily during the time of onset. Now, also a disclaimer not to discount other processes that are present or prevalent during onset. This is just one of the things along with it that is prevalent. Yeah. So what happens is there is a small residue that remains, and therefore it is OLR which will dominate subsequently, the impact of clouds on OLR. So given a certain cloud cover, any further changes in clouds will not have an impact on alpha S minus OLR. ERA 5, yeah. No, I have also validated with series, and they are consistent. Although there is difference in cloud cover and how clouds are in series and ERA 5, the results are consistent. So now here is this graph which shows through radiative perturbation calculations how OLR is influenced by different parameters. Why OLR? Because we have seen that is an important parameter during onset. Okay, so black is OLR difference between South Asia and Sahara. This is from ERA 5. Okay, straight away, simple difference between these two regions. Now, there is quite some detailed, nuanced analysis that has been done, which I'm not going to touch upon. If there is interest, we can discuss about that. But it has been aligned to onset date. Okay, there are three more curves. Red represents the effect of temperature. Gray is cloud, impact of clouds, and blue is the impact of water vapor. Now, this has been aligned to onset date. All of these has been aligned to onset date. So just before, a few days before onset, there is some slight increase in impact of cloud. But even before that, water vapor impact increases first, and then clouds take over. So this is proof of the mechanism which I showed earlier. So going forward, water vapor has an impact on the clear sky OLR. Yeah, this is onset. Just a few days before onset, there is first increase in this thing, clouds, impact of cloud on OLR. So monsoon onset has not yet occurred, but some small pre-monsoon showers are occurring. So that impact you can see here. But even before that, the blue is closer to black, and subsequently gray becomes closer to black. So basically, there is a period before onset, few pentards before onset, when water vapor is having a greater impact on OLR, and then clouds will have a much bigger dominant impact on OLR. It does not mean water vapor does not have an impact. It just means that clouds will have a slightly larger impact. So there is this transition that occurs sometime slightly before onset. So the mechanism that I showed is during this phase here, when water vapor is slowly building and it is having an impact on OLR, and yeah. So yes, okay. So here is once again from ERA 5. This is OLR clear sky. Okay, this is only clear sky. Both the y-axis. X-axis is two different variables. There is column integrated water vapor and surface temperature. Why? Because these are the two variables which have an impact on clear sky OLR. These determine how much radiative cooling is occurring in the clear sky. Now, there are two regions I have considered. Circle is South Asia. The plus is Sahara. Let us start with Sahara. The different months have been colored. So this is pentad green. Now, over Sahara, surface temperature and clear sky OLR are a linear function during most of the months. But the relationship between OLR and column water vapor is not so strong over Sahara. If you look at South Asia, relationship between clear sky OLR and surface temperature is also linear during non-monsoon months. So if you consider these months, May, June, July, August, September, that is from pinkish to brown, orange, purple, so that's this way. It is during the monsoon months that this relationship breaks down between clear sky OLR and surface temperature. During those months, water vapor has a much stronger impact. So water vapor begins to have an impact once it crosses a threshold of roughly 20 to 25 kgs per meter square. So since Sahara does not cross that threshold, it remains within the regime where OLR clear sky is determined by surface temperature. But over South Asia, water vapor increases substantially, and clear sky OLR becomes a function of column integrated water vapor. So here is another way of doing the same thing. Clear sky OLR over Sahara, this is for South Asia. Now this is OLR, total OLR, effect of temperature, effect of water vapor. So you can see, yeah, sure, please. Yeah. So water vapor absorbs the emission from surface and then re-emits at a slightly lower temperature.
So, but then the absorption would be larger than the emission. It should have been a positive impact other than the negative impact.
So,
what I mean is that larger the water vapor,
yeah.
it will have a larger absorption rather than emission.
But it will emit from much higher altitude because the scale height. Yeah. Hmm. Yeah. Yes. 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 So, no, I'm not sure if I understand this correctly.
So see that if you increase the cloud,
Yeah.
make your weather,
Yeah, because it's very high. Yeah.
weather when you increase the water pressure.
Yeah.
So
It,
what you are saying is that your absorption, yeah, you will have increased absorption.
yes.
But then it is not because of the emission from the top, right? It's just because of the
Yeah.
absorption.
It is because of the absorption. It is absorbing at one particular band and everything else. Yeah. So, yes, this is total spectral OLR. So, one particular band is absorbed by water vapor, and in that band, it is emitting from slightly above. But yeah, you're right. It is the total. Yeah, that is. So here you can see that temperature over Sahara is closely following the total OLR. Water vapor has no impact, some slight impact. That is what you see over here. Uh, now, over South Asia, OLR has a very weird behavior. It increases during non-monsoon months, and then come monsoon, it suddenly goes down and then does this dip. So temperature is consistent during the non-monsoon months, water vapor during the monsoon months, right? So this is clear sky OLR only. So the key takeaways from all of this, sorry. First of all, monsoon and deserts can be thought of as a balance, systems where there is a balance between radiative heating and low level convergence, so dynamic radiation circulation systems. So one of the important things is the water vapor radiative effect, which already nudges South Asia away from what Sahara is progressing towards. So that is where already things begin to diverge in this system. So we also highlight internal feedbacks in monsoon. Most of the focus is on how external factors affect monsoon. There are internal feedbacks within the monsoon system itself. This is one such feedback. So what if, so this also brings me to a question. What if we are able to push enough water over Sahara? Will we get a monsoon over there? So the answer is yes, and we do have one interesting simulation where Earth's rotation is reversed. So that changes large scale dynamics. And so let us begin with the bottom plot. This is column integrated water vapor in colors, and the arrows indicate the moisture flux, column integrated moisture flux. You can see substantial moisture flux into uh, moisture advection into Sahara and very large precipitation over that region. Now, this is happening despite very high albedo. So conventional theory tells us that Rodwell-Hoskins mechanism, we have strong monsoon over here in the normal world, subsidence to the west, so you have deserts over here. In the reverse rotating world, the subsidence would be to the east. Now there is nothing, no subsidence on this side, but albedo is very high. Because albedo is high, there should not have been a monsoon over this region. Albedo is high, F2 will be negative. That is uh, that has been the theory since Charney. But look at this. The control has very high albedo. That is where the albedo of the retro begins with. Over about 300 years, it gradually declines. That is because of growth of vegetation in this region. F2R is negative in control, climatology. The very first year, when you reverse rotation, F2R becomes positive, and then it gradually increases. And corresponding to that, you have an increase in monsoon in the very first year itself, although albedo is very high. So this is a proof that albedo is probably not as important. If you can control F2R, you can have monsoon. So this is the very first year. X-axis is days now, and y-axis is F2R. Control in thick line, and dashed line is retro. So during the non-monsoon months, it is similar. Divergence during the monsoon months. No difference in shortwave absorbed. All of the differences are in the OLR. So this is a very different way of thinking about the same system coming from that same equation. So the takeaways, once again, a second takeaway covering some of these aspects, is that earlier theories focused too much on albedo. They suggested albedo as a limiting factor in monsoon. But in my opinion, F2R is a much more appropriate parameter. So F2R positive is a necessary condition for monsoons to exist, and F2R can be positive, or if you can modulate F2R with albedo or with OLR, right? So it is not just albedo, but you have to consider OLR as well. So with that, I will stop here. Thank you.
Just previous slide.
Yeah.
The last statement.
Yeah.
I can also flip it around and say
Huh.
the existence of monsoon is the reason why
For F2R to be.
oil are to be best and bad.
Yeah.
So this is a classic framework.
It is.
So I don't think you can say concentrate.
I cannot. Yeah, I cannot. I I only want to say that in, yeah, probably I should frame it. Yeah, probably I should frame it in this way that F2R positive and monsoons exist together. Yeah. Yeah. It's a diagnostic framework. So yeah, I agree with that. Yeah. Right. Yes. That is true.
But even then, what if you can include water buffer to a region, then you can start.
Yes. So that's, yeah. In
Starts with the water buffer.
yeah. Yes. That is one way of having monsoon. So that is one proof. Yeah. Yes. Simulation for the reverse rotating world only. Everything else was from era 5. Yeah.
The topics in general,
Yeah.
yeah, so you can easily
Yeah. Yes.
And what about the meta things? They do they become instead of
Uh,
I don't understand.
yeah.
Whether it should be reversed.
Yes. They do become easterlies. They will. Yes. Yes. Yeah. Yeah. No. If I change albedo in. Okay. Given the Indian conditions remain the same. So when Rodwell-Hoskins mechanism only suggests that there will be subsidence somewhere over here, and so probably except for that region during the monsoon season, you will probably have arid climate, but during the rest of the time, probably there will be some local precipitation. Huh. Yes. Right. I got that. So that will change the latitude of ITCZ over here. Yes, it will go slightly to the north, but this region will continue to be arid during monsoon season because of the diabetic heating over here. Only this particular region. The remaining regions probably will have some local small scale precipitation. That is something we see over here in this part. So this is now arid during the time when monsoon exists over here, but vegetation continues to persist. So albedo does not become as high as Sahara over here, although this is an arid region. Why? Because during winter season, it receives rainfall, so vegetation exists. Not rainforests, but there is vegetation. Now, during the monsoon season, there is no rainfall. But there is enough moisture for the vegetation to survive through the monsoon season, and then come winter, it will get enough precipitation during that season. So albedo is high here, and still you have arid region. So yeah, so this is something similar to what you were asking. Yeah.
For the Sahara.
Yeah.
It's like ancestral,
No, that is only during winter. During summer, there is no clear subsidence coming out of Hadley cell. No, no. In the zonal mean, you will see some subsidence, but not in. There is subsidence over Sahara. There is subsidence, but that is because of radiative cooling, and not linked directly with the Hadley cell. So during the summer season, there is ascent over here, and the summer Hadley cell is further north, and it goes all the way back. So you have a very clearly defined Hadley cell. Summer Hadley cell, but the winter Hadley cell, which creates the subsidence, which should create the subsidence, is not so well established. I mean, not so well established, especially in these regions. So the subsidence, that's a zonal mean picture, not, yeah, yeah, yeah. Okay, thank you. Okay. Question online.
Am I audible?
Yeah.
Am I audible?
Yeah, you are audible. Please ask the question.
Yes, I'm Harpreet. Hello, Bhaiya. Interesting work. So I don't know, I would have missed it, but this is related to the onset, monsoon onset, the um, uh, temperature difference between two regions, Sahara and North India. I want to know that how does it behave during the monsoon season?
Sorry, is it possible
Uh,
for you to type the
and
question
once
so
you
we
have
can?
mentioned it, I would have still, if you can. Uh,
Hello, is it possible for you to type the question?
uh, my
Audio is
voice
not
is
very
coming.
clear.
Hello. Sure,
Okay.
sure, sure. Okay, I'll type
Just
it.
repeat your question.
Thank you.
Okay. Maybe can you please write your question, and maybe I will take it after the session, after JS session.
Yeah. Yeah. Okay, I'll just go to the first part, which is partly covered by Chetan. So if you look at this today at 11 o'clock, the satellite data, you can see that a lot of clouds in Bay of Bengal and rainfall also here. Entire East China, Southeast Asia. So it's a very peculiar feature that land regions are not able to get the rainfall, but all the ocean regions, Pacific, this is very interesting, connected to what you were saying. Okay. Now, as you pointed out already, onset is progressing well up to this point, but notice that on this side, it is way behind. It should have been here. Okay. So this part has not been highlighted. The only doubt I have, I've asked many people, I don't know the answer, how do they draw these lines when there's no data? Please find out. I'll ask many people, Rajiv, and nobody gives me an answer. Over land station rainfall data, you can have a criteria, but over ocean, how do they do it? Just they draw a line through this. Okay? So I don't know. Okay. this is till yesterday, so we are well below normal, and today also, that is 10th morning also is below normal. And you can see the interesting east-west difference, okay? Most of the dry regions are on the east, and this is, I think, not monsoon connected, because monsoon has not even come to this point. There's something to do with mid-latitude, some system, okay? Now, this I like, this was the onset of El Nino, okay? I'm sorry, what happened? Okay, that was animation from satellite data, which supposed to show sea level moving from here to here from March to May. Some was not working. So the beauty is, you can see the Kelvin wave moving from west to east in the satellite data beautifully. You can't see it in SST. Sea level is very sensitive parameter, and they are able to measure within a millimeter. And you see a nice wave traveling. You can look it up in their website. Okay. Now I'm going to talk only about one paper which just came out last month, actually in April 30th. This is about this year's monsoon. Now I'm really impressed that today we are able to get a paper about this year's monsoon so fast. Okay. But note, this is a new journal. Okay. You guys are in trouble. There are so many new journals. I don't know how you keep track. Okay. So one of the purposes of this monsoon cafe was to get ideas about various papers being published. There are too many of them published. So this paper is a very good paper. And they are arguing that this year, in the month of February, there is a very unusual pattern. Okay. What they call a ring pattern. Okay. Of high temperatures, both in South and North Pacific. And of course, this is going to ultimately come up. So the interesting thing about this paper is that this is another view of that. Warm North Pacific, warm near US, and then warm equatorial Pacific. This is what they're talking about, and cold in between. Okay. Now, so they mark this in their paper. They call the first, second, and third. This is a circle they are identifying. This is unique. It has not happened before. Okay. Now they have done a nice thing. They have compared various El Ninos in the past 30 years. Okay. You can see none of them are similar. Okay. And this is the most unusual. Somewhat some 2050, but not quite. 20 did not have this part. So they are saying that this El Nino is very different from all the previous El Ninos, because the spatial pattern of SST anomaly is very different. Okay. So the point they're making is, most of the time we explain the buildup of El Nino through the warm water volume. That is a standard practice. But they make a point, in the past 2 decades, the buildup of the heat content is insufficient to provide short-term prediction. So their argument is, things will go wrong. If you had a model which worked well 20 years ago, it won't work well now. Okay? Now, this is a point you're making. You look at the depth, heat content with depth, okay? And this is SST, okay? You can see clearly that these 2 years are quite different from these 2 are somewhat similar to this, but 23, if you recall, the El Nino was expected, but it came after the monsoon, so we were lucky. Now, what I like about this paper, which is what I think I would highlight, if you depend only on observation to understand, you'll never get anywhere. You'll get correlations, it won't help you, because there's not sufficient observation. If you depend only on model, you're in trouble, the model may be wrong, okay? So that's why they've taken one model and then various experiments, okay? In one of them, they maintain climatology here. This is the region which is active. So I won't go into detail, you can look it up in the paper, okay? Now, the other thing, this is a point they're making. In this 20-year period, okay, the warm water volume increased, the Nino 3.4 responded fairly quickly, late response from here to here. Here you can see it happened very quickly. So they're saying this El Nino is going, we have different from other El Ninos. Okay? Now let's see what's happening. According to CDAS data, the value of Nino 3.1 was 1.153 in June. Okay? Now that's a bit misleading. This is not relative El Nino, this is the standard calculation. So you have to subtract 0.5, then you'll get around 0.8. Okay? This is what CFS is predicting in the month of June, little bit above 1. Okay? I think this is also, I think it's not relative El Nino. The point is, it may go up to 4, which has never happened before. So one can talk about super El Nino if this evolves this way. Okay. Now this is from the IITM website. In June they are saying close to 1 point, and then they are going flat. They are not showing much increase. So as far as we are concerned, we are only worried about September. It reaches 2 and then it starts increasing. How about DMI, IOD? It is still close to 0. It's increasing, and this is what they are predicting. Again, maybe in September you will have an impact if this is correct, but this is not easy to predict. Now let's look at how good the forecast was last week up to 8th. Not very good. I would say they started okay, then they predicted an increase. This is NCMWF, not CFSV2. They predicted a huge increase in rainfall from 4 to 7. It didn't happen. Okay? And so that clearly says that the short-term forecast in the later part, starting on May 30th, we all know that. The first week is okay, next week is a little bit not bad. Now, this is what they are forecasting the coming week. You can see that this is itself not sure, they may be wrong, but this is what they're predicting that by June 50th, they will further come down. This means that monsoon onset will not occur in North India for the next 20 days. This is a disaster. If you have been anywhere in Delhi and Kanpur, I have been there. It's a nightmare if the onset doesn't occur. And as a matter of fact, a very interesting story going back to 50 years ago, related to what you were saying. In 1 year, I remember, monsoon was coming late, people getting desperate. There was no AC those days. They have AC now. So one retired meteorologist, maybe became slightly crazy. He suggested everybody put up a big pot and boil water to get water vapor going up. That's what he's talking about. Okay, it's not feasible. Mechanism is right, but human being cannot compete with nature. The amount of water vapor you need to pump up is so high. North India has no water now. They are waiting for water to come. Okay, so you cannot do that, but that's how we argue. Okay, now let's look at the MJO. One of the reasons why there's a delay is MJO is causing positive OLR anomaly over starting from here June 6th and then June 9th, June 10th. You can see we are in this phase now. Once the MJO effect goes away, then it's about 12 days from now, there is a chance of this system moving up. Now this is a forecast already shown by Chetan. I won't show that, but I want to look at this forecast. This is starting on 3rd June. This is this period. Okay, so it's correct. All of them are negative. Okay, except the South India. And then next week, the coming week, South India will not be so good, but neither is North India. So the monsoon essentially is not here, not there. Is weakening. Okay. Now go to the 12th to 18th. Sorry, there's a mistake there. I'm sorry, I made a mistake here. There should be, no, there's a mistake. It should be 18th. I made a mistake here. 18th to 25th, this is the last week. You can see that there is some hint of central India in the next 2 weeks. But this itself is doubtful. We'll see that why. This is the NCMWF. It says there is no monsoon till July 1st week. Okay? So we'll see who is right. Is it NCMWF or IMD? And this, again, is very bad news for people staying in North India. No rainfall till July 1st week. Now, let's see who else agrees with that. Now, this is ECMWF, okay? Their forecast. This is this week, showing clearly that monsoon is not moving beyond Karnataka. It's stuck there, okay? And there was a nice system of positive anomaly right across to East China, okay? But they also make a prediction 1 month later, which I'm surprised, but that's very surprising. This is about 1 month later. Okay? This is even more bad news. If up to 20th July, North India doesn't get any rain except for some parts of Northeast India and maybe Bihar, Chhattisgarh, all these areas will have huge crisis because they are expected to get by this period some rain. Okay? So I hope this could be wrong because 1 month forecast, we know weather forecast is not accurate. Okay. Now, but this is not consistent with their long-term forecast. Long-term forecast based on 1st May is here, 1st June is here. Let's look at this. It says that in July, it is going to be slightly below normal. Okay. June is well below normal, which would be right. We know that. July is not as bad as June. August not bad. September is bad. So this is the Eastern Bay forecast. So I would think that there may be some interesting thing here. This is consequence of El Nino really strengthening in September. So this is a clear possibility. But this part is where right now their own long-term forecast is not agreeing with their short-term forecast. So I'm not sure what's going on here. It's the same model, but they get different. Okay, now let's look at some tables V2 for whole of, based on June 1st week, whole of July, totally negative. This is millimeters per day. This means about 4 millimeters per day. Okay, this is very large. Remember that July rainfall is 9 millimeters per day. All India. Subtract 4. You're below 50%. This is what happened in 2002 July. So that we may have a repeat of that, which will be huge disaster. This is the prediction by, I mentioned this, James 2, there's a Canadian model. I hope they are right. They're only predicting about 1 millimeter below. That is manageable. Okay. And this is multi-model mean, North American multi-model mean. They are close to CFSV2, showing very high negative anomaly here. But notice this part. This is what I'm interested in. East Asia and China are doing very well in July. India is doing badly. Okay. Now, anybody is thinking about air sinking from El Nino, I would like to know what's happening here. Okay. It's not affecting this region. Okay. Although it's affecting Indonesia, but India is affected much more. Now, this is all the pie in one look. There are models like TSM NCAR model, which is showing that eastern part of India may gain something in July. But many models are showing, this is Canadian model. So this is ensemble mean. This is what you saw in the last picture. Now, this is what I showed traditionally, comparing Eastern BF to the next 1 week, 14 days, all of them are saying monsoon will not proceed beyond this. Okay? It is actually stalled at that point. Okay, so before I close, I just want to mention interesting thing about last year. Last year is the only year I know of where all the months were above normal. Okay, that's very rare. Normally, in a monsoon season, 1 month is bad. For example, take a beautiful example here. June was very bad in 2019, but September made it tough. It was unusual by IOD process, and then it was one of the highest. Okay, and in most years, you can see 1 month will be below normal. Last year was special. I don't know why, but look at the previous year, both at the same seasonal mean. Here, June was below normal. It was made up by August, September. But 2025 is what you call the ideal thing. It was above normal all the four. I don't know why. Nobody has figured it out. Okay, I'll stop here. And if there are any questions? If not, next week's speaker is Mohit Singh. He's not here right now, I think. He's going to talk about snails. Now, that's a mystery. Find out why he's talking about snails. What is that to do with monsoon? Okay, think about it. Thank you.